So today we're going to continue talking about applications of the chain rule, and our big application today is called implicit differentiation. So we're going to start by doing a little bit of review of functions and what they look like. We'll talk about how to do this new thing called implicit differentiation, and finally we'll see another application of it to another key skill called logarithmic differentiation. So we often talk about functions, and we often talk about a function being in explicit form. So a function is called an implicit form if it has the form of an equation that has not been solved for a dependent variable, but it sure could be if we took the time. So here we have an equation, x squared plus y squared equals 1, and hopefully you recognize it as the equation of the circle. Again, x is going to be dependent, y is our independent function, and if we wanted to, we could take the time and we could solve this for y. And here we would get an explicit function. It's a function that y, our independent variable, is equal to something that's just in terms of the dependent variable. We only see x's on the right hand side there. And what's actually neat is here we actually have two functions. So we actually have two functions, as I said. We have the function y is equal to the positive square root of 1 minus x squared, which gives us all the positive values here on the top half of our circle. And we also have the function y equals negative square root of 1 minus x squared, which gives us all the points down here on the bottom half of our circle. So we do actually have two functions, and now that it's in this form, we can take the derivatives. So what we have is we have the derivatives here, and these are fine looking functions. They're not so bad. It's just a little bit of a chain rule to get them out. The issue is that to get to these point where we can take the derivatives, first we had to solve for y, which can be daunting. This can be a little challenging. And then the second step is we had to take the derivative. So what we're going to discuss today is a way to hopefully stop and avoid that first step of solving for y. We want to figure out how we can take the derivatives right away. If we look at this circle, it makes sense to talk about the slope anywhere on the circle. It makes sense to talk about the slope anywhere on any sort of weird curvy shape. So why don't we just go ahead and find a way to take the derivative without having to solve first. So let's start by reviewing some derivatives in the forms and notation they take. So in this case, what we have is we want to take the derivative of x cubed with respect to x. So the dx tells us our dependent variable is going to be x, and inside here we have a function of our dependent variable only. And so since they match, what we do is we just go ahead and we take the derivative following our very normal power rule, and we get 3x squared. So nothing so bad here. We follow our power rule. So similarly, we can take the derivative of now sine of x cubed. The difference here, of course, is that now what we have is now we have a composition of functions. We have an inside function sine of x. We have the outside function cubed. So when we take the derivative here, we're going to need to use our chain theorem instead. And so our chain theorem says, well, it's not so bad. Take the derivative of your outside function, leave that inside function the same, and now multiply by the derivative of the inside function. And so when we simplify this down, we end up with just 3. We leave that sine of x alone, and we multiply by the derivative, which is cosine of x. Not too bad. Again, we can look at another example that's very similar. So let's recognize that we still have an inside function in this new derivative of f that kind of matches up with our sine, and the cubes match up. That's our outside function. So when we go to take the derivative, we do the same thing we did before via the chain theorem. We take 3, leave that inside alone to the squared, keep that f of x in there, and now we need to take the derivative of f of x. Well, I don't know what this function is, so I just kind of stop working. I say that this is just the derivative of f of x. Well, what about when we want to take the derivative of y cubed? So what you want to think is you want to think that y is a mystery function of x. It depends on x. It's an independent variable here. So when we can't quite take its derivative, but we can if we just follow this idea of the chain theorem. So the chain theorem again says now y is our inside function, cubed is our outside function, so when we take the derivative, we write 3 leave the insides alone, which is y, and now we multiply this by the derivative of y. And what we usually do here is we can usually shorten this notation up just a little bit by writing this as 3 y to the squared power times our notation dy over dx. So dy over dx is our shortcut notation for the derivative of y with respect to x. These are the same ideas. But it follows the same basic pattern as the chain theorem follows before. We take the derivative of the outside function, leave the inside function in the composition the same, and then multiply by the derivative of the outside function. So let's try to take the derivatives of a few more complicated expressions before we move on. As always, I encourage you to pause the video, try to take the derivative yourself, and see what you get. Okay, so let's try it together. So the first thing to recognize here is we're adding together two things, and we know that derivatives work well over addition. That is, you can just break this up into the sum of two separate derivatives. In the first derivative, well, since the variables match, this means we're just going to use our normal power theorem. So the derivative here of x squared is 2x. In the last case, since the variables disagree, what we can see is we can't use our theorem here. Instead, what this is this is just going to become the derivative of y with respect to x, because these things mean the exact same thing. So this is the same idea. It's just we're going to take the derivative, but we don't know what the function is. And then this will just be our answer. So in this example, again, pause the video, take a few seconds to try to see what your gut tells you how to take this derivative. Now what some people try to do is they think to themselves, well, this y, maybe it's just a constant. Because if y is a constant, then you would write that this is just going to be equal to y. The problem is this is not quite true. It's true that if you had to take the derivative of x times 3, you would sure get 3. But in this case, what we need to do is we need to take the derivative of a function x times another function y. So this means what we need to do is we need to use the product theorem. So remember that the product theorem says that we need to take the derivative of our first function, x, times, we leave that second function alone, and we're going to add to this, keep our first function the way it is, multiply by the derivative of the second function. So in this case, the derivative of x with respect to x is going to be 1 times y plus what we have here is going to be x times dy over dx. We can't do anything more here because we don't know what this function is. It's a mystery function, but it'll just be dy over dx. So what we're going to do is we're going to take derivatives of functions using what's called implicit differentiation. So basically what this means is we skip solving for y first. Okay? We solve for y later. So what we want to do here is we want to find dy dx, that is the derivative, for x squared plus y squared equals 1, and we want to do it by not solving for y first. We just want to go for it and take the derivative. So the first step is to differentiate both sides of the equation with respect to x, that is the independent variable. So what we're going to do is we're going to take the derivative with respect to x of x squared plus y squared, and this is going to equal the derivative of 1. And now we want to go through and take the derivatives. So on the left hand side, this is going to break up into two separate derivatives. So the first will be the derivative with respect to x of x squared, plus we need to take the derivative with respect to x of y squared, and all of this will equal the derivative of just 1. So in the first one what we have here is when we take the derivative here of x squared with respect to x, we're just going to apply our power theorem, which gives us 2x. Plus now we need to apply our chain theorem. So our chain theorem says we're going to have 2 times leave the inside function, that is y, all by itself, now raised to the first power, multiply by the derivative of y with respect to x, that is the derivative of our inside function. And this will equal the derivative with respect to x of 1, which is just going to be 0. So the whole key here is right here we had to use the chain theorem because y was a mystery function. So what we're going to do now is we're going to engage in a lot of steps that basically are solve for dy over dx. Okay, we want to get the derivative by itself. It's just solving an equation as usual. It's just there's a lot of steps because there's a lot of things that can go on here. So the first hint is to collect all terms involved in dy dx on the left side of the equation, move all the other terms to the right hand side of the equation. So if we see here, we have this 2x over here. We need to move it over to the right by subtracting it from both sides. So we'll subtract 2x from both sides, and we'll end up with a simplified equation. 2y dy over dx is equal to 2x, is equal to just negative 2x here. So here I've copied my equation up on the top of this page so far. So it's still 2y dy dx is equal to negative 2x. So the next step in this process is to factor dy dx out of the left-hand side of the equation. So in this case, if we factor that dy dx out, we're just left with a 2y as the other factor. And finally, we solve for dy dx by dividing both sides of the equation by the left-hand factor, that is 2y, that does not contain dy dx. So basically, we've solved for our derivative is equal to negative 2x over 2y, which simplifies down to negative x over y. And so you can say, well, why did we do this? And we did it because this is a really equation to use to figure out the slope at any point. If we look up here, say at the point 0, 1, well, we get negative 0 over 1 has a slope of 0. Definitely, nice slope of 0. What happens if we look down here at square root of 2 over 2, negative square root of 2 over 2? Well, if we put these numbers into our derivative formula, we're going to get that we have a slope of 1 right here on our circle, and that seems to make sense. And so this is a lot easier to use actually than the previous square root formula we found before, and this technique is a lot easier to use for most functions. And of course, as always, there's the very important step 5, grimace, and move on to the next problem, and you may want to remember how to spell the word grimace for a quiz or something. So let's go ahead and try out this idea of implicit differentiation for something a little more interesting looking here. X cubed minus xy plus y squared equals 7. So this function has a pretty neat graph over there, but let's just follow our steps. So step 1 says we need to take the derivative of everything, so we take the derivative of both sides. So we put x cubed minus xy plus y squared into the derivative, and this will equal also what happens when we take the derivative of just 7. So as always, pause the video and think to yourself, well, what's this going to be? So if we work through this, what this is going to do is it's going to split up into 3 separate integrals. So we have the derivative of x cubed minus the derivative of xy plus the derivative of y squared is equal to, well, let's just take the derivative, it's going to be 0. So for the first derivative here, when we take the derivative of x cubed, the variables match. So we're going to get 3x squared minus, we have a product rule in here, but we did take the derivative of this earlier in the video. And earlier in the video, we found this was going to be y times 1 plus x times dy over dx. And last, we have to take the derivative of y squared. So this will be 2y dy over dx equal to 0, and that comes to us from our chain rule again. Step 2 says what we want to do is we want to collect the terms with dy dx on the left hand side, and the other terms need to get moved to the right hand side of our equation. So what we'll have is we'll have x times dy over dx, negative, plus 2y dy over dx is equal to y minus 3x squared. So there's a little bit of algebra here. Pause and make sure this makes sense to you, but these are how the terms get moved around. The third step says we want to factor that dy dx out. So we want to factor these terms out. So what we're left with is a dy over dx times a negative x plus 2y still equal to y minus 3x squared. Step 4 says we want to get dy dx all by itself, so we need to divide. So we end up with dy over dx, that is our derivative, is going to equal y minus 3x squared all over negative x plus 2y. And so what we have is we have the derivative here, and this is neat for many reasons. First of all, well, we didn't have to solve our original equation back here for y. I don't even know if I could solve that for y. I mean, I'm sure someone could, but I don't know how to do it. But we still end up getting the derivative, and the derivative is fairly simple. Putting in the x and y coordinates anywhere along this curve here will tell you the slope anywhere you want. Not a bad formula overall, and it wasn't a terrible amount of work. Now one might not only want to find first derivatives, but second derivatives of equations. This is not a bad thing to think about having to do, so let's remember what this means. So to find the second derivative of dx squared means what we need to do is we need to find the derivative of the derivative. Well, we figured this out earlier. Recall, we found that the derivative in this case is going to equal negative x over y. So this means we need to find the derivative of this, and we know how to do this. Now the issue, of course, is we're going to need to bust out our good old friend, the quotient theorem in this case. So in this case, everyone sing your song in your head as you go. So we need to take the low times the derivative of the high function minus our high function times the derivative of the low function all over the low function squared. So simplifying, we end up with just negative y plus x times dy over dx all over y squared. And you may think, hey, I've done it. This is good. We're good to go. One last thing we want to do, we want to replace dy dx. We know what dy over dx is, so let's go ahead and replace it. So this means it's really going to be negative y plus x times negative x over y all over y squared. And this is our second derivative. Usually second derivatives aren't too bad to find, as long as you've already done the work, of course, and found the first derivative. But here we go. This now tells us not only the slope, but if this was a position function, this would be our nice acceleration. And of course, you could simplify this if you want, but we'll be okay. So our last big idea from this section is called logarithmic differentiation. So let's recall a problem we faced just a few days ago. So just a few days ago, we were faced with problems that involved natural logs of functions, and we wanted to find the derivative. So this means that the derivative of this function involves taking the derivative of this big natural log of stuff. And one of the things we said was, well, what we should really do is simplify this first. So if we simplify this, because what's going to happen is now we can take the natural log of x squared minus the natural log of x minus 1 cubed, which looks a little better. But by using properties of logs again, what we can actually do is take an even easier derivative of these quantities instead. So overall, even though it looked a bit cumbersome to begin with, using properties of logs we can simplify quite a bit the object we have to take the derivative of until it becomes, well, rather easy to take the derivative. Not so bad. So using logs really helps us avoid quotient rules, product rules, chain rules, whatever you want to talk about in terms of having to use these other ways. So suppose we wanted to find the derivative of this equation that didn't actually start with logarithms. Well, what we could do is we could start by taking logarithms of both sides of the equation. And so what we end up with is the natural log of y is equal to the natural log of x squared over x minus 1 cubed. And you could ask yourself, well, what in the world did I do this for? That doesn't look much easier to work with. The next thing we want to do is we're going to use these logs to simplify things. So on the left we still have natural log of y. There's usually not a lot that's going to happen over there. But on the right hand side we can break this up first into two separate logarithms using the division property, and using the power property we can simplify this down quite a bit as well, because those exponents just come down in front. And now finally we get to differentiate both sides. So on the left we're going to take the derivative with respect to x of the natural log of y, and on the right we're going to take the derivative of everything as well, 2 ln of x minus 3 ln of x minus 1. And what's nice about this is the derivative of the natural log of y, well, it's going to be 1 over, leave the insides alone, times the derivative of the inside, which is dy dx because of the chain theorem here. So this is our good chain theorem and implicit differentiation. And this is going to equal these derivatives we can do separately. So this first one is nice and easy. It's going to be 2 over x minus 3 over x minus 1. And what's nice here is we have dy dx here. Now we just have to solve for it. So now all we have to do is simplify, that is solve for dy dx. So this means that dy over dx is going to equal y times 2 over x minus 3 over x minus 1. And what we can do is we can replace with our original y, which was x squared over x minus 1 cubed times 2 over x minus 3 over x minus 1. And what we did is we avoided the quotient rule, we avoided a complicated chain rule, we avoided doing a lot of other things by using logarithmic differentiation. And so just to reiterate these last two steps, we solved for our derivative, and here we replaced y with what we knew y was originally way back at the start of our problem, x squared over x minus 1 cubed. So here's a fun one. Again, we want to find the derivative of this function, and you can go ahead if you want and do the chain rule, a nice little triple product theorem there if you want, but what I'm going to do is I'm going to use logarithmic differentiation. So I encourage you to pause the video and try it for yourself first. So step 1, we take the logarithms of both sides. The natural log of y is going to be the natural log of this whole mess of stuff. And we can simplify this down, of course, by breaking it up into 3 separate logarithms. And the reason we want to do this, so this was steps 1 and 2 really. Step 3 now says we take the derivatives. So on the left hand side, when we take the derivative, we need to take the derivative of the natural log of y. And on the right hand side, we need to take the derivative of the rest. So now when I go ahead and take the derivatives, on the left hand side I get 1 over y times the derivative is equal to, well, 1 over x squared plus 1 times the derivative of x squared plus 1 is 2x, plus 3 over x minus 3 plus 1 over x minus 2. And steps 4 and 5 all simplified together. This tells me that my derivative is equal to y times 2x over x squared plus 1 plus 3 over x minus 3 plus 1 over x minus 2, which equals, when we're all said and done and I replace with all my y's, x squared plus 1 times x minus 3 cubed times x minus 2 times, in parentheses, 2x over x squared plus 1 plus 3 over x minus 3 plus 1 over x minus 2. That's my derivative. Now, this seems like a bit of work. I don't disagree. But it would be so much more work to go through all the product rules and chain rules with stuff like this, okay? I promise you. This is a lifetime-saving device. As always, try the problems on Blackboard. Actually, it's a handout this time. Post a question and take the video quiz, and I'll see you in class. Thanks.